Hello, gentle readers, fellow Earthlings. Today from our desk with Ross Finlayson, December 11th, 2024, is another episode of Logos 2000. A monologue of sorts, a dialogue of sorts, a study in research and foundations, 21st century foundations. And so today, what I thought to do was to look to the books that we've been looking at in the previous episode a little bit, and one of them was Ogden Rood's The Theory of Color. And so I kind of enjoyed looking at that a little bit because it helps to explain things like colorless green. When we think of terms of the monochrome and the monochromatic, and of like one shade of a color. And so then when green is kind of to be understood is that it's in the one sense there's like all the different pigments that reflect green or absorb red and blue on either side, or according to the theory, and that there's others that there's kind of the absence of color, and it's kind of like not gray, that the gray scale and green scale in a sense make for the luminosity channel, and has that there's of a colorless green. That when I read that from Rood the other day, it struck me. It reminds me of a quote one time that was said to be parsable or not. It said, "Colorless green ideas sleep furiously." And it's when you think of that, you say, well, that's kind of a contradiction in terms, colorless green. At the same time, it isn't. It's actually part of the thing. It's actually part of this dual tri-stimulus color space that there's a color. It's a colorless color called colorless green. And so it begins another thing. As with regard to sleep furiously, I'm not quite so sure what that's supposed to mean, but usually the rapid eye movement stage is achieved at some point in time during sleep, hopefully, and it accomplishes kind of recycling the lymph and glymph inside the skull case behind the blood-brain barrier with regards to the drainage tank of the cerebral spinal fluid, and these kinds of things that modern dogma is just getting to understand and recognize again is part of the act of everyday respiration and metabolism every night with regards to the recuperative powers and the necessity of a good night's sleep with regards to health overall, and then the maintenance of homeostasis, holding oneself together in one piece, kind of usually is with regards to that being for the matters of the circulatory, that the lymphatic and glymphatic and the circulatory, or each circulatory networks to be sure, of the physiognomy and the physiology of the usual mammalians of the primate variety are found in almost countless abundance all over the face of Earth, fellow Earthlings. So let's take a look at that a little bit and see what more we might gain from it. Then what I thought to do is also to read some more from, or to begin to kind of just quote some passages from Owen Wilson Richardson's, a Nobel Prize winner of the early 20th century for physics, his great book here, The Electron Theory of Matter, which, while a bit passé in its style and some of its notation and the names of things, is yet thoroughly quite modern, and also that he addresses a lot of the things that usually get left out, that are because to try to solve things are taken from a particular fixed perspective, and that to keep things linear and in so few words tractable, and as for fungible and as sensible, fungible, and tractable, that it has a lot going on with it. So this is a programming manual, pocket reference that was looked at the other day, and just with regards to that, the art of computer programming is a title of a series of books by Donald Knuth, a great and eminent computer science professor, and also with regards to the concrete mathematics a bit more concrete than applied mathematics. The concrete mathematics gets into things like recurrence relations and many combinatorics and counting arguments and all these kinds of things to do with number theory and algorithms. As with regards to the art of computer programming is a great series of books. And I'm not sure exactly when it was mentioned here at some point in time, but if you ever do find any kind of typo in one of Knuth's books, apparently he has a standing offer to remunerate the finder of these errata 88 cents or something along these lines. That it's not always so easy to find those in the main works, but you can find something like in his notes upon Alan Iverson's computer programming language, is with regards to that being a very specific, technical, specialized programming language whose source texts are much symbolic. And so of its own kind of thing, APL, a programming language. And then there's another one in that fascicle that is a note on the Stirling numbers, the Stirling cyclone subset numbers, and which are kind of like the choice function, the cyclone function and the subset function, to give combinatoric counts of how many cycles or subsets of these things according to the permutations and what they have. The Stirling numbers, and then with regards to things like the factorial and stuff like that, it's possible to find at least one typographical error in this kind of thing. And so this with regards to programming and computer programming, it's kind of like Bill Gates one time. He said, anybody who can read the art of computer programming is up there with people who work at Microsoft. And so I worked there before, and some of the other large .com or tech outfits as a software development engineer, usually just under my own direction to get some stuff done in accordance with these things, to become familiar with systems with tens of thousands and millions of lines of source code, and up into the gigabytes and terabytes of all these things, and on the scale of past one transaction per second, which in a sense is kind of large, with regards to the crankety things of all the distributed systems, the information systems, and these kinds of things. That it becomes kind of sensible when you consider something like the Windows source code, like Windows 7. It's only like a couple thousand files, and it's only like 50 or 60 megabytes or something like that just by itself. It's not much bigger than Linux in a sense. And when it comes to reading the source code and coming to terms with larger bodies of code, is for reading something like, it's not quite the same as like, let's read data, let's read the tables from the CRC Handbook of Chemistry and Physics, with regards to lookup and these kinds of things that arrive at all the derived values for these measured or given parameters, the constants for these quantities. And then for things like that, or for like, let's consider the 1,500 modules that make up a retail website system, or something along the lines of, the master execution scheduler of manufacturing for a rather large concern. It's got hundreds and hundreds of programs. And by programs, what I mean by that is like contract programs with a program office that run like a large manufacturing concern all by themselves and all for themselves. And as with regards to, where do we find those 12-inch floppy disks that have been gathering dust for 50 or 60 years? Well, you got to figure it out. Sometimes there's all that's left is the numbers. That anyways, computer programming is really based upon literacy to achieve code understanding and the ability to understand the interactions of these large kind of systems. That if it wasn't for the fact that literacy and the comprehension had been acculturated for a long, long time, then I'm pretty sure that I would not have been qualified to do the work that I did and do. So it's these kinds of things sometimes that go to help to affect, to reflect, to relay that reading is fundamental So here in Rood's Modern Chromatics, we'll try to pick up where we left off. It was about colorless green. So it was in leaves, and so in the plants, the plants are green, and they're kind of like brown or green, and so it's usually according to what the presence of chlorophyll, and so chlorophyll is a pigment, and then chlorophyll sits in these what they call photosystem type 1 or photosystem type 2 of the photosynthesis. And what photosynthesis is it's a metabolic pathway in plant life with chlorophyll as with regards to the conversion of sunlight and the energy in it to via a metabolic pathway according to this pigment, according to these donor electrons and these kinds of things, what arrives after the photoelectric effect, according to the intensity of the optical light and the photosynthetically active radiation, that there's only particular bands of radiation that interact with these the red or the yellow of these kinds of aspects of the different bands of the photosynthetically active radiation, the colors that affect having the correct energy and the correct input to make it so to be able to drive photosystem 1 or photosystem 2, a couple different types of little organelles of the plant, usually on its leaves, as with regards to, or if it's blades, as it were, of sort of like grasses vis-a-vis bushy plants or woody plants or leaved plants, vis-a-vis weeds and these kinds of things, plants, that then what is green and what is green is kind of two different things, as Rood here is kind of beginning to detail. The green color of vegetation offers a rather peculiar case. When we examine with the spectroscope any ordinary green pigment, we find that the red is absent and the blue and violet much weakened, as was the case with emerald green. Green leaves, however, furnish a spectrum of a different character. The extreme red is present, then occurs a deficiency of colored light. It's colorless, which is followed by an orange-red space. Next comes the orange, then the yellow, greenish yellow, and yellowish green. After this follows a little full green, the rest of the spectrum decreases rapidly in luminosity. There's a figure. The sum of all these colors is a somewhat yellowish green, which is accordingly the color presented by green leaves in white light. It will be shown in chapter 10 that a mixture of red and green light furnishes yellow light, which explains the production of a yellowish green in this somewhat singular way. It follows from the analysis just given that green leaves are capable of reflecting a considerable quantity of red light, where surfaces painted with green pigments would not have this power and consequently would appear black or gray. Hence, under the red light of the setting sun, foliage may assume a red or orange-red hue. Corresponding to this, when the illumination is of an orange color, foliage will partake more of this hue than would be the case with ordinary green pigments. Connected with this is also the great change of color which foliage experiences according as it is illuminated by direct sunlight or by light from the blue sky, the tint in extreme cases varying from a yellow or slightly greenish yellow up to a bluish green. Simler, Simler, has constructed a simple and beautiful piece of apparatus based on the singular property which living leaves have of reflecting abundantly the extreme red rays of the spectrum. It is called an erythroscope, erythroscope. A plate of blue glass stained with cobalt is to be procured, having a thickness such that it will allow the extreme red of the spectrum to pass, but no orange or yellow. It should also transmit the small band of greenish yellow. A plate of rather deeply colored yellow. This should be capable of transmitting all the light of the spectrum from the farthest red up to G. That is to say, it should cut off the violet and blue violet only. When a sunny landscape is viewed through these two glasses, it assumes the most wonderful appearance. All green trees and plants shine with a coral red color, as though they were self-luminous. The sky is cyan blue, the clouds purplish violet, the earth and rocks assume various tints of violet gray. Pine trees appear of a dark red hue, orange or yellow flowers become red or blood red. Greens other than those of the foliage are seen in their natural tints, or at least only a little more bluish. Lakes preserve their fine blue-green coloring, and the play of light and shade over the landscape is left undisturbed. The whole effect is as though a magician's wand had passed over the scene and transformed it into an enchanted garden. For the full realization of these effects, it is essential that stray light should be prevented from reaching around the glasses, and accordingly the glasses should be mounted in an arrangement of wood or pasteboard which adapts itself to the contours of the face and excludes as much as possible, kind of like to avoid snow blindness with regards to like glacier goggles and these kinds of things. On comparing the spectrum given by the blue and yellow glasses with that of the green leaves, it will be found that the two glasses cut off almost all the green light furnished by the leaves, but allow those green rays of light to pass which the leaves are incapable of supplying. Colorless green. So with regards to then that being about like that light, that's the light kind of falling away from this frequency, and the light kind of coming towards this frequency, is about this second spectrum of light. The idea that there's light has a spectrum of these colors, and diffraction and refraction and reflection is simple. The diffraction and refraction are around and make the optical part of this the action of light. Kind of like when the sun is behind my head here, and it comes around. That accordingly, when it just barely is beyond the limits of what blocks it in front of it, all of a sudden a great image of it comes, as if it makes its image apparent around, showing that optical light affects then the sensors of the CCD pickup at the camera to make it so that it is as of the optical character of light and the special nature of the free passage of the information and the signal and the intensity even in light, in energy, in this manner, free if metered by, it's called light speed, according to a finite speed given it this massless otherwise. As with regards to light and optical radiation, that being different than electromagnetic radiation, where it starts getting involved instead, that the wavelength of this wave of these rays is for the velocity up to light speed, which is limited because there's a tiny bit of non-relativistic mass presumed in an electron. And so that most of its mass otherwise is relativistic according to its high velocity, and that it's rotational velocity, the electron in its usual model of beta particles as a stream of electrons, or in current in as with regards to electrical current, and then as with regards to radio waves in the electrical field, those being their own thing too. That these are things that Richardson in his book 100 years ago has already had, is like, these are all these empirical things that definitely are part of it. So with light and optical light, and the idea that there are two kinds of green attaining to each other in the middle of this monochromatic luminosity only. With regards to like albedo and reflectance, how bright and shiny something is, or otherwise how this is, it's kind of like so. One of the ideas that has come up here before is the idea of Maxwell's demon, and this is like, explains the law of thermodynamics, that you couldn't have just like a little gatekeeper in a box with particles that let the higher energy particles through and kept lower energy particles in, that just resulted automatically making a temperature gradient between these two, just by the random nature of the particles letting the higher energy particles through and keep the lower energy particles in. Yet it's not entirely unreasonable to figure an optical effect that would make it so, where the idea is you want, in the summertime, you want the higher intensity light to reflect. And and in the wintertime, you want the lower intensity light to absorb, so that there's kind of a natural reflective account for passive cooling, not heating, passive cooling, and a natural kind of account for passive heating, just absorbing energy from light. And so the idea is to make it so that light that's efficient enough to be strong enough to make it through. You just point it at a reflector, and then it will bounce itself back out. And light that is not quite so strong will you just kind of divert it the other way. That you can have a mechanical device, because light will go on the medium according this way. That it's possible to design a surface coating for like the roofs of buildings, so that it automatically kind of gains in the summer, and you just kind of give it the value so that it's according to solar intensity in the summer and solar intensity in the winter, and so that in the summertime it would reflect more, and in the wintertime it would absorb more. Sort of a eudaemonia, a roofing eudaemonia. kind of like the supercapacitor, they don't really have that yet in kind of the usual idea of things. But as kind of as explained by a simple physical optical effects, which are, pretty well understood, usually only one or the other of those is kind of figured out. And you just make to, in these days, more to reflect the heat and achieve passive cooling, say. So reading on into Rood, and he talks about the prismatic, then the chromatic, because metal, like a prism is a piece of glass or plastic, and it's shaped so that the different reflections and refractions. For example, here's a toy one, and the idea is that as light shines through it, then that it will affect to reflect on the surrounds. And so this isn't as good as the one I had before, but it's just one I have here it's just an example, and there's kind of the prismatic effect of it just from looking through it and from shining lights through it and so on. And so that's with regards to what was, Newton's experiments and all these kinds of things, and Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. And that these days sometimes they say, well, it's indigo and violet, we're going to kind of keep them the same. And because as Rood, for example, is mentioned, is like at the ends, it kind of alternates. It alternates what the order is of those. It kind of has on the outside of the bounds of that both of the kinds of alternations of perceived color and by frequency and wavelength even in the optical light. So it's prismatic of the prism. Then the chromatic is kind of reflected in as like, what's the reflections from metals? Why are metals a special kind of material? Because, well, they're kind of like liquids, frozen liquids, And the thing about metals is that they're conductors, and so all the electrons move rather freely among them. And it's like somebody said one time, it's something about like, a metal is just one big atom. And what they meant by that was, in a sense, that some of the other aspects of what's the atomic model and the nuclear model and the atomic model kind of become structural and become more as the molecular, or here the crystallographic of the metals, which don't really observe crystallography in them usually, as with regards to otherwise minerals and lattices of materials. With regards to materials, though, the prismatic and the chromatic here affect to reflect these two different ideas about light and color. And that it then getting into these things that it's also as for the second spectrum and fluorescence and phosphorescence, the emission of light, and then with regards to then how things are absorbing or reflecting light, that these are different ways and different things that go on it. And so that's all said to be optical. So optical usually just means with regards to the eye. But then the difference between that and geometrical is that rays travel in a straight line. And then what they do when they meet something is they act like as a mirror image, they reflect. And then diffraction and refraction and refringence then become other factors and features of optical light, visible light, that are the most amazing sort of experimental setting according to these things, because it enables the perception of the observational effect, and it's largely whereas sound can affect to make very dynamic changes in the shape of a signal, or as with regards to the content of a signal, vis-a-vis the phonemes and the spoken word, and that being very natural, and that these days the graphical presentation is very much aided by all manners of the rendition of any kind of information or signal as an image. There's that then of these kind of senses with their intromissive and extromissive senses, that they are both very much passive and active in these kinds of things. And then that we have these models of propagation that, because transmission and propagation speeds are finite, where in Newtonian gravity or something like that, there's the usual idea, at least in Newtonian theory, that something that's infinitely far away, almost, that still moves at all, automatically affects the entire space and time. With regards to then whether in relativity theory, where there's this fixed and metered and not quite free transmission of information, light speed being finite, that anything massy at all cannot achieve this speed, does not have that gravitational waves arrive in real time, in zero time. That in various theories that are like Newtonian, that they do. So that then has, again, this light's in the middle, and it's got its spectrum and its flux. It's constantly the flux side of, otherwise the flow side of all these fluid models of substances and essences and materials and current and all these things, the flow, and then the flux. That above that, then light has these secondary aspects, is what in the middle makes for why optical light is special, and it's kind of central in terms of dynamics of the system. For that, then, intelligent actors of any sort can take information so gained by transmission of signal, for example, communication and agreement, to arrive at means to affect great change. The dynamics. So, with that said, then the chromatic here, Rood here gets into metals and what's going on with what's reflected in what is colors. A quantity of white light is reflected from the real surface. Belong with it is mingled a certain amount which has penetrated a little distance into the substance of the metal. And there is undergone reflection. This last portion has a color. If we cause this mixture of white and colored light to strike repeatedly on a metallic surface, for example, such as gold, we constantly increase the proportion of light which is penetrated on the surface. A process of this kind takes place in the interior of a golden goblet, hence the color on the inside is deeper and more saturated than on the outside. And he talks about the difference between like silver, where it doesn't, silver, which is a perfect conductor almost, but which it doesn't reflect much. And it says, the true color of metals must not be confounded with that which is often given to them by the presence of a surface film of oxide or sulfide. Such films cause for the most part a bluish appearance, though all the colors of the spectrum may be produced on metals in this way. In fact, the hue in these cases is due to an interference of light caused by the thin layer of oxide. It's quite distinct from the actual color of the metal. There are a number of explanations as with regards to why the sky is blue. There are a number of explanations, and they kind of tend to align. And then with regards to something like the rainbow, there was Carl Boyers wrote a great book about the entire history of trying to figure out what makes rainbows. And it's called The Theory of the Rainbow, or The History of the Rainbow. And it has, for example, where its name come from, the arc-en-ciel, this arc in the sky, and with regards to the theorists of the time that arrived at why rainbows have the colors that they have and why they have the angles that they have. Like Descartes was given is that's one of the things that Descartes actually made as an applied mathematician and a physicist, why Descartes is considered, a relevant for being able to make an applied sort of physical theory. And then also, but it really gets into Airy and Young. So Young is most known for electron physics. So Millikan and Young and Thomson, how that Young was a really great scientist. I don't know his last name, or forget it. But before the time of Rood here, but a few decades before, so if I'm not mistaken, and Millikan and Thomson. And Thomson basically was really great into electron physics, J.J. Thomson. And then Millikan kind of just refined and bettered his experiment. It gave better numbers, a few more digits precise, or a few digits closer. That Airy, A-I-R-Y, after Descartes, had significant contributions to the theory of how rainbows form and a mathematical account of what the angles are. And so similarly, then Boyer in his book, and that author, he's a historian, and he's best known for the conceptual development of the calculus, where he outlines the concepts that came into being to make it so that Newton and Leibniz had this great priority dispute about the fundamental theorems of calculus and about the infinitesimal analysis that resulted the integral calculus that we have today, the integral and differential calculus. That Boyer is really a great, and so that if you're going to read some history, it's recommended you read Boyer's conceptual development of the calculus. Then Motz and Weaver have their a story of science and a story of mathematics. There's stuff like Eric Temple Bell's Metamathematics, and that's kind of popularization. But and then there's of course these days the wiki and all these kinds of things. Yet then, as with regards to that the conceptual development of the calculus is considered one of the better books on the history of the development of calculus. Here we kind of start from Aristotle and even before, because Archimedes and Pythagoras end up having to figure out calculus to means of exhaustion and methods of exhaustion. And the things like the infinite limit and these kinds of things, those names for these things come from those times. That for today, when we have something like Weierstrass and delta epsilonics, and having a formalism that's acceptable compared to something like Maclaurin's incredible work called infinitesimal analysis, about the time of Newton, he kind of wrote it up and made it palatable. Then with regards to the survey, that Maclaurin's book is perhaps one of the best kind of sole sources of the thing. Kind of like this electron theory of matter is of 1918 or whatever, and then that was like 1518, 1618, 17. It was like hundreds and hundreds of years ago in the time of Newton. That's Maclaurin's infinitesimal analysis. And then about 1900, there's stuff like, Price's infinitesimal analysis. And then it was changed to reflect to call it instead real analysis. And then it's usually often kind of piled upon that, encumbered, called complex analysis. But that's not really necessary to achieve analyticity in real analysis. The chromatic, then, back to color, and the prismatic and the chromatic. So for the additive and subtractive colors is a thing, and for filters and pigments, reflecting the additive and subtractive color as a thing, or vice versa. And then this is part of like art enrichment classes, like for children, because the color wheel is introduced to like elementary school kids as part of art enrichment. And so when it comes to that, it's a critical part of the theory of physics to come along later when someone says, well, how did TV screens used to work? Well, they use red, green, blue, and today they use luminance, chrominance red, and chrominance blue, colorless green, if you will, YCBCR. That then to know the additive and subtractive color spaces, the theory already changes that from like a mind-boggling thing. It's like, well, of course everybody knows that. Everybody's known that since elementary school. We learn that, and it's theory and explain things, and it'll always be true. It's science for our art, and then also matters of perspective and projection, and everything that's necessary to give somebody a fundamental approach to geometry also comes from that. So just let it be said that whereas art is just matters of the applied, can be any kind of different thing, that for the theory that there are certain crucial and critical segments with regards to the conceptual development that are as part of usually matters of the practice of rendering things in perspective and the mixing of paints, and with regards to then the filters and the actions of light. Another thing about light that's really profound is when there's an eclipse or something like that, because you can look at like the shadows of leaves, and during the eclipse they all gain this kind of extra extra halo. It's just, and it's not like a round thing. It kind of follows their shape. And then the shadows have all these speckles of light in them. The light is profound. And the optical and imaging is profound. When you observe during like an eclipse, according to the passage of the motion, that the actual face of the body, like the moon, will spin around. It's incredible, and it's real. It's just optical. It's just as a matter of fact that are these rotating bodies, that it has redshift bias, and what that means is that the light comes in and goes around. It's coming around, as with regards to why all these effects are readily available to experiment with basically zero cost materials, and that everybody has most otherwise usual apparatus, and it's directly phenomenological. So this just goes to help to affect to reflect that the Sky Survey was, of course, the great laboratory for all of before modern optical astronomy, radio astronomy, electromagnetic astronomy, gravitational wave astronomy, all these different kinds of astronomy, and then also with regards to data and the collection for the operationalist and instrumentalist things that we can't see with our eyes or with our senses, that there's still to be cultivated and acculturated all the stuff that is still just directly phenomenal and is still super classical in its result, that is super classical and directly phenomenal. So everything from mirages on the road to mirrors and all kinds of things with regards to these, as with regards to the optical character things, and that light is special and it's kind of central. It goes without saying that we don't want then later the theory to kind of have that, well, way up above, we kind of just have it live in the electromagnetic radiation theory. That's not the only place where it lives. It lives in the surrounds of that, and it's central in that too. So that's a nice thing, I think. So the prismatic and chromatic, though, is what I wanted to establish that Rood's getting into here with regards to the theory about 1900. Then he talks about the perception of color, pointillism, shapes, diagrams, optical illusions. When optical illusions are real, vis-a-vis optical illusions that are perceptual, with regards to the left, right, and up, down, and then also the spherical aberration and eyeballs, and parallax and peripheral parallax. These are things. Not all optical illusions are merely illusory. Some are perceptual. And he talks about Maxwell. Maxwell is very well known for electrical theory, and he also studied color theory, and Newton. And here he talks about Young and Helmholtz. So Young was mentioned, and he talks about how a palette of pigments can come up with lots of different colors. It's kind of like in sound and the ability of a musical instrument to represent relative tones, and then via overtone to kind of synthesize the presence or absence of tones, and then especially when it's acculturated to relate it to well-known tunes, the tones, that it's possible to make perceptual off of things like a representation of the full gamut, the range from limited to palette, the constituent elements, that those in their mix and their blend and their application with regards to shadow and the surface can make a lot of effects visually or as well as mentioned aurally to these matters of representation. And then it's not merely just as a matter of artistic expression, like what is this? What is this? It's actually is like this is what it is as well. So that gets into a lot of different things, and that, for example, many of the reasons of the success of modern imaging standards is to discard many elements that kind of fall beneath the perceptual, yet that in comparing them to an actual real optically blocked image, a real image, would be very, very, very detectable. Vis-a-vis something on this screen these days could be manufactured from any of many, many things. Yet that even such aspects as the representation after ray tracing of visible light, and how like light will in its diffuse character according to its a direct account makes for these things, that the theory of that is still coming a long, long ways. And these sorts of accounts on the theory of light are still very much apropos today. And people should know them, because when you get way, way up above, and it's just like, we have energy and we have a particle wave model, and so this is our electromagnetic rays that are waves, dot, dot, dot. That's at least 3 different things, then each one of those empirically is built up from all these prior accounts and all this other descriptive and true stuff that goes into the theory. These facts have been known to painters since the earliest ages and furnish the foundation for the so-called theory of 3 primary colors, red, yellow, and blue. So in inks, you'll see cyan, magenta, and yellow, and black. So this is called CMYK or CMYK. And so like when you have a printer, it's got cyan, magenta, yellow, and black. And sometimes it'll have 5 or 6 colors in a usual color printer. The idea being that the combinations of those result something that reflects from these pigments, reflects these colors. The primary colors of red, green, blue are the emissive colors. And then this gets into additive and subtractive colors, each one's of those. So you have emissive colors and reflective colors. So this is also helping to affect or reflect that there's always kind of a two-way or a dual tristimulus color space. And it's usually left out of accounts when otherwise it's just kind of like, this will make it look like on the page, or this will make it look like on the screen. A rendition, according to what the eyes will find and what a colorimeter can detect, colors. If we look at the matter from a theoretical point of view, we reach at once a conclusion that it cannot be true. The theory of existence of 3 fundamental kinds of lights was a previous sort of theory. Nevertheless, it will not be difficult to show this quite without foundation. So a previous theory kind of had like, well, there's pigments. Well, they didn't have so much in the way of filters and these kinds of things. Airy, Maloney, and Draper alone dissenting. So Brewster's spectrum, he is like, there's only red, yellow, blue. And then Airy, Maloney, and Draper help to provide that there's more than that. But it's kind of an elementary account of what can be used to then make renditions of things. But as with regards to that being like true to life is not so. Then he talks about Maxwell's discs. Another way of making this experiment is simply use a fragment of window glass of good quality, as was done by Lambert and Helmholtz. Now this reminds me of the fact that quartz glass is a very particular thing with regards to heat and with regards to electricity. That with regards to light, it's just kind of simple. It looks kind of like glass. But quartz is a particular crystallographic thing, and as with regards to electricity, and heat, it's a very good insulator. Yet it also has these ways that electrons move. So that's something I just want to mention, that these are 3 different things that are related together. Then the heat is like reddish light, and it's like as if you heat an iron bar to its melting point, it begins to emit a dull, hot red light. And then with regards to something otherwise that's optical, then it kind of goes up. Then blue and violet and indigo kind of reflect these different ways that it's out on the other side of optical light. And then the electromagnetic stuff and its wavelengths is just way, way, way beyond that. whereas also X-rays and microwaves and these kinds of things are kind of like at these various approaches and these levels of these things. Microwaves, the science oven, not for food use. So anyways, taking a look here, this helps this book very much to figure out this theory. The celebrated Thomas Young adopted another view. According to him, each minute elementary portion of the retina is capable, each minute elementary portion of the retina is capable of receiving and transmitting 3 different sensations about the nerve fibrils. So then we kind of come up to rods and cones, or when we were studying Feynman a little bit, he was talking about the omatoma, or of the bee's eye, and then also with regards to the frog's eye. And that just helps to affect or reflect that besides rods and cones, then there are also pigments in the eyeball, and so they reflect very particularly differences with regards to what people can see of colors, with regards to what's in the filters or in the pigments, as it were, that are not necessarily part of the usual theory, but as a matter of fact are part of the theory. That is kind of a funny thing. From Helmholtz's great work on physiological optics. And what he shows is curves showing the action of the different colors of the spectrum on the 3 sets of nerve fibrils. And one's at the lower frequencies, and one's at the higher frequencies, and one's in the middle frequencies. So together these help to detect changes with regards to like edge and level triggering and these kinds of things, rising edge, falling edge. And he talks more about the theory. So this book this is a great account of according to physics, the theory of what makes imaging, and also what affects to reflect the perception of color and the production of color, and for materials, how to affect to describe and theorize how it's possible that these things come together, and to make it like so. Very beautiful investigations of this character have been made by Helmholtz, Maxwell, and J.J. Mueller. Talks about gray. That I'll be looking some more at this book. Ogden Rood's the book on the theory of color from this time, about 1900, and as to why it's a significant work that helps to affect to reflect as a survey, and it has a great descriptive accounts of what these things are. We're talking about the photometric comparisons of changes of a light, and with regards to the monochromatic, which is kind of like a particular contrived thing, like lasers are monochromatic. Monochromatic light is like an LED produces monochromatic light. It isn't really natural in the sense that sunlight is, or that incandescent bulb provides. That an incandescent bulb was long affected to be the same in a sense as sunlight, although then otherwise particular lamps were found to have frequencies that are much more like the photosynthetically active radiation for the production of plants or grow lights, and that these days also they have LEDs, and it can be found that those can drive photosynthetic activity, and also that the photosystem receptor basically has like a 1% duty cycle, like each little stoma or photosystem activates and then kind of rests while it recharges, and then that's just constantly going on over the surface of the photosynthetic surface according to the pigment chlorophyll in them and the photosystem. That then it's possible to like take an LED and turn it on and off like a million times, but leave it mostly off per second or per minute, to use like a lot less energy, but still to be always driving all the photosystem receptors. So kind of like this idea of like, I want a roof that's reflective in the summer and absorptive in the winter. This one's like, I want something that's gonna like send a laser. It's like a laser grow light that turns on and off 1,000 times a second, but still grows just as fast or more. It's constantly driving the photosystems at full duty cycle with the most efficient application of electricity to make light. See, science. Having now considered the changes when it is very luminous or very feeble, we proceed to study effects. And so this is just more of the accounts of the range of colors, the visible colors, contrast, modern chromatics and contrast. And so that also reflects on like the ideas of the optical illusions and contrast. Small interval and gradation that has to do with like the continuous tone and these kinds of things. In some mountain lakes, such as the Königssee, we find the blue-green water actually passing in some places by rather quick gradations into a purplish red. The rapid transition to this almost complementary hue produces an effect which seems strange and almost incredible to those who for the first time behold it. When the cause is recognized, we learn to look upon the purple patches as marking the shallower water. Having accepted the effect as reasonable, we soon find ourselves enchanted by it, and always remember it for its strange beauty. This is relevant for, you know, light and matters of perception and perspective, and also about how light travels cosmologically, and like why does light travel like it's massy as according to a gravity well. According to general relativity and special relativity, it's like it follows the geodesy. That's what it does. And it does, and it's close, but it's not all the way there because it actually bends a little bit more than that. So when it was discovered, it's like, well, the theory of relativity predicts it's like it's less than half off what is found to be the aberration. That you'll find the word aberration very often in optics, and what it means is unexplained. And so that it was known what the aberration was, and then relativity theory was able to arrive at saying, hey, this fixes that. And it's like, well, great, how does it fix it? And it's like, well, now there's only half left of what was off. And so this is better and it's accurate, and so it's a good theory. I mean, it's not wrong, it's in the right direction. And so then trying to also figure out, it's like, well, what does Fresnel say to make it so that it's like the light that comes around, kind of rolling over the focus, as it were, and then around, actually makes it the rest of the band that it makes? Is here that's called Fresnel large lensing, vis-a-vis notions like the gravitational lensing and to help explain, and that's part of the account of redshift bias and removing redshift bias. The color which next to green acts most powerfully on the nerves of the eye is violet. After that follows blue-violet, artificial ultramarine blue. So when we talk about purple, indigo, and violet, and ultramarine is getting into which one of those is red, which one of those blue, and which one of those is green, you know, as with regards to, or in colorless and this and that, as with regards to, for the infrared catastrophe, that's being the new one, that the old one after Rayleigh-Jeans, where Rayleigh-Jeans are pretty much all about the black body radiation and the computation of, for electrons and photons to balance each other out as particles, energy-wise. That Rayleigh-Jeans is like the great thing that led to this whole ultraviolet catastrophe, and then, you know, picking for spectroscopy, how these things are to be, and saying that that's a good theory. It's a very successful theory, and it's great. then for this infrared catastrophe is the idea is like, well, now let's take it back from the other perspective and then how that comes up, and also for this optical character of the second spectrum as it goes out past the optical range. Because beneath the optical range is just infrared and heat. But then beyond the optical range is the ways it goes out. And so then that's called, for electron physics here, that's called neutrino, muon, and Large Hadron physics, part of the infrared catastrophe that goes from making a continuum mechanics again the theory of physics. There is one, and so that's what I'm calling it, because those are the names for it they have for these different pieces of it, and it's good to have them in one theory. Pairs and triads of color. Neutral gray. Color is less important than form, but casts over it a peculiar charm. Here he's talking about color in painting and decoration. So the theory has a lot going on, and there's much yet to be known of it. There's much yet to be known of the theory of light at all and its superclassical behavior and effects. The electron theory of matter. This is what I've been reading, because he'll be working on like this whole theory and building up electron physics. And they'll say, oh, by the way, of course, we know that this is where we have this other side of it too. And furthermore, this is great how we're doing it. And then also the theory will include this other part as well. So Richardson won't be called wrong later for being like closed-minded about things, because he's very familiar with the electrical theory. And so as he's trying to come up with a theory where it's kind of like, instead of waves and particle waves being the particle conceit of things, it's kind of more of like an electrical thing. We like, well, what is primary? Is it matter or is it charge? And it's like, well, either really, they kind of are complementary as with regards to unification energy and stuff like that, with regards to super-symmetry and that. But yet at the same time, with regards to them defining each other versus mass and charge and the velocity of light and the lifetime of a neutron, they're kind of reflecting this tetrad of quantities, proton, electron, photon, neutron, and these for these fields, that then it kind of reduces from 4 fields down to 2 fields, and that thusly then it can be kind of one or the other of those with regards to mechanics or electrical theory. Either way, all kind of one theory that in this, all these great formulas that it comes together. So Richardson comes up with the Laplacian, and then the Gauss's theorem, or Gauss-Bonnet as it's usually called, or Gauss-Bonnet, B-O-N-N-E-T. And then there's Green's functions and Green's theorems, and then there's about Stokes, because Maxwell arrives at E cross B or D cross H and these kinds of things with regards to then which of Maxwell's laws is considered real and the other one derived, or which one's, as he puts it, fictitious. Richardson explains fictitious in the introductions of things that are like, well, this is on the outside, so we can't say it adds in or else it would add out. So we'll call it fictitious and just say it's equal and opposite. But on the other side, that's what it looks like to hear, that these two sides of the mirror are yet like inverses, whatever. Kind of like I was reading this Tinkham's book on group theory, which is pretty great. So this is about group theory of particle mechanics and quantum theory, and it's by a guy named Tinkham, Tinkham, and he's all about like group actions and symmetries and stuff like that. And he helps explain, it's like, well, yeah, these tensors carry all this stuff right around like vector addition, except for the inverse, which is anti-symmetric, because it's symmetric from the inside or something like that. That it helps to explain that the mathematics has a lot going on that's geometrical and here hypergeometric, with regards to those being the the aspects of supersymmetry and the hypergeometric kind of. I mean, and by kind of, I mean really, mathematically and in the physical interpretation and thus in the model of the things, as it were. That then in the account of after Laplace's formula, where you take the Laplacian and then have that being equal to 0, so it makes it like Lorentzian. And then as with regards to Gauss, that it's like this is flux and flow, because we can figure it out for a surface, but it's really through the whole volume of the thing. So it's kind of a way to make a dimensional reduction, kind of like the whole hypercube thing is like, let's make a dimensional reduction from having blown up all its values. This is just one, and like it's in 3D space, and then we have 2D surfaces, and it's called Gauss theorem, and it's definitely always used to equivocate, to make equivalent what is this term as regards to current across surfaces. And then Green's theorem, and as with regards to these things, that Richardson provides a very great amount of the mathematical formalism that goes into the infinitesimal amount. Then what it's arrived at is Poisson's equations. In rectangular, then spherical, then rectangular, then polar, then spherical coordinates, as up into all kinds of matters, the definitions of at least 3 kinds of electrical intensity, and light is different, a description of how light is different, yet it's still kind of how and why it's arrived at that it's called electromagnetic radiation. The properties of waves, rays, waves and rays, waves as rays, Brewster's experiment, Bucherer, in the Annalen der Physik 4, volume 28, 1909, about condensers, a particular kind of interesting electrical component, and all these kinds of things, and then just built-in trigonometry and analysis, and a bit of function theory. So we're going to be looking at that a little bit here. And then this is just a little book on the essentials on the theory of functions. Well, gentle readers, I hope you have a great day, and I'll wish you well. So long.